Welcome to Civil Engineering Edge, where we simplify complex construction concepts for students, professionals, and curious minds. Today, we dive deep into prestressed concrete, a modern engineering marvel that enhances the strength and durability of concrete like never before. Whether you're designing bridges, buildings, or industrial structures, understanding prestressed concrete is essential for modern infrastructure. In this video, we'll explain what it is, its principles, materials, methods, applications, and pros and cons, all with clear visuals and practical insights. So, grab your hard hat and let's get started on this engineering journey. What is prestressed concrete? Prestressed concrete is a specially engineered form of concrete in which internal stresses are intentionally introduced to counteract external loads. Unlike conventional reinforced concrete, which resists tensile forces through steel bars alone, prestressed concrete uses tension steel tendons or cables to pre-compress the concrete before it is subjected to actual loads. This pre-compression increases the concrete's ability to withstand tension and cracking, making structures lighter, more durable, and able to span greater distances. The concept combines high-strength steel with concrete's excellent compressive properties to deliver optimized performance in structural applications. Prestressing is commonly used in bridge decks, flyovers, multi-story buildings, water tanks, and railway sleepers. Its ability to reduce the amount of concrete and steel required makes it both an efficient and economical construction method, especially for long-span structures. In simple terms, prestressed concrete is concrete that has been preloaded internally, so when the actual service loads are applied, the structure remains strong and crack-free. Principles of prestressing. The core principle of prestressing lies in applying a pre-compression to the concrete, which neutralizes or reduces the tensile stress developed under service loads. Concrete is strong in compression, but weak in tension. To overcome this limitation, high-strength steel tendons are tensioned and anchored, inducing compressive forces in the concrete. When external loads act on the structure, they must first overcome the internal compressive stresses before producing any tensile effect. This technique delays or eliminates the formation of cracks and increases the load-carrying capacity. Prestressing can be achieved using two main methods: pre-tensioning before concrete placement and post-tensioning after concrete has hardened. In both cases, tensioned steel tends to compress the concrete member, optimizing its performance. This principle ensures a more efficient material usage, enhanced durability, and reduced maintenance over the structure's lifespan. Materials used in prestressed concrete. Prestressed concrete relies on three primary materials. 1. High-strength concrete. Concrete used in prestressed members should have a compressive strength of at least 30 MPa or more, as it must resist initial pre-compression and applied loads. 2. High-tensile steel tendons or cables. These are typically strands, wires, or bars made from high-carbon steel with yield strengths ranging from 1,500 to 2,000 megapascals. They are responsible for inducing the internal stresses. 3. Anchorage devices. These are used to anchor the steel tendons in place. They consist of wedges, bearings, and plates that transfer the prestressing force to the concrete. Insert 3D image prompt. Hyper-realistic 3D rendering of materials used in prestressed concrete. High-strength concrete cubes, steel tendons, and anchorage system laid out on a construction table. These materials together form a composite system that enhances structural efficiency, flexibility, and lifespan. Methods of prestressing. There are two major methods of prestressing used in the construction industry. 1. Pre-tensioning. In this method, steel tendons are stretched before the concrete is poured. Once the concrete gains sufficient strength, the tendons are cut and their force is transferred to the concrete via bond. This method is usually employed in precast elements like railway sleepers, beams, and slabs in factories. 2. Post-tensioning. Here, ducts are placed in the concrete where steel tendons will go. After the concrete has hardened, tendons are inserted through the ducts and tensioned using hydraulic jacks. Once the desired force is achieved, they are anchored at the ends. Post-tensioning is more flexible and widely used in cast-in-place applications like bridges, high-rise buildings, and parking structures. Both methods aim to induce beneficial compressive stresses, preventing tensile cracks and enhancing durability. The choice between them depends on project size, location, and execution methods. Application area of prestressed concrete. Prestressed concrete finds its application in areas requiring long spans, reduced deflections, and crack resistance. Here are key sectors where it is extensively used. 1. Bridges and flyovers. Long-span bridges, elevated highways, and flyovers utilize prestressed concrete to minimize the number of piers and allow for better load distribution. 2. Buildings. Multi-story buildings and office complexes often use prestressed concrete slabs and beams to create larger open spaces without intermediate columns. 3. Water tanks and silos. The circular shape of tanks and silos benefits greatly from prestressing, helping resist internal hydrostatic pressures and reducing wall thickness. 4. Railway sleepers and metro tracks. Prestressed concrete sleepers offer greater stability and longer life under dynamic loads. 5. Industrial structures. Structures like chimneys, transmission towers, and cooling towers often rely on prestressed members for stability and durability. Overall, prestressed concrete is ideal for structures that demand strength, longevity, and minimal maintenance. Advantages and disadvantages of prestressed concrete. Advantages. 1. Higher load capacity. Prestressed concrete can carry much greater loads than ordinary reinforced concrete, allowing for longer spans and slender sections. 2. Reduced cracking. Internal compressive forces prevent tensile cracks, leading to improved durability and structural integrity. 3. Material efficiency. Less concrete and steel are needed for the same strength, reducing the dead weight and material cost of the structure. 4. Greater span-to-depth ratio. Suitable for architectural and infrastructure designs requiring uninterrupted open space. 5. Improved service life. The reduced tendency to crack makes the structure more resistant to corrosion, moisture, and environmental effects. 6. Versatility. Prestressed concrete can be precast in factories or cast in place on-site, depending on project requirements. Disadvantages. 1. Higher initial cost. The use of specialized equipment, skilled labor, and high-strength materials increases the upfront cost. 2. Complex construction requires precise engineering design, quality control, and expertise in tensioning systems. 3. Limited field modifications. Once tensioned, modifying a prestressed member is difficult, making design changes challenging. 4. Maintenance of post-tension systems. Especially in corrosive environments, post-tension ducts require careful grouting and sealing. Despite these disadvantages, the long-term benefits and savings in maintenance and materials make prestressed concrete a preferred choice for modern infrastructure. Thanks for watching. Now you know how prestressed concrete revolutionizes modern construction by enhancing strength, reducing weight, and increasing lifespan. If you found this video helpful, don't forget to like, share, and subscribe to Civil Engineering Edge. Got questions or want us to cover a specific topic next? Drop your thoughts in the comments. We love hearing from you. Stay tuned for more insightful content that bridges theory with real-world construction. Until next time, keep building your knowledge brick by brick.